thank you everybody for joining this morning, and welcome to today's panel discussion on high reliability in harsh environments. As electronics manufacturing expands into new applications, of course, an increasing number of harsh environment applications ranging from EV to down-hole and aerospace seem to be raising their head. This panel will discuss the materials and strategies to protect electronic assemblies in these conditions. I'm delighted to be joined by David Greenman from Humiseal. Hello, David. And Dave Hillman from Hillman Consultants. That's not quite the right name, is it, Dave?
Yeah, I've made a very long, it's Hillman Electronic Assembly Solutions, but Hillman Consultants will work.
Okay, and then we have Chuck Bauer from TechLead Corporation. He's joining us from California, where it's actually fairly dark over there. So he will get lighter as the debate continues. So thank you for joining us from actually, I think it's Oregon you're in, isn't it, Chuck?
That's correct. Yeah.
Yeah.
Doesn't really matter. It's West Coast.
That's true. That's true. Okay. So I'll get off with my first question. Let's see how we get on with this. Harsh used to mean things like down oil wells and some aerospace applications. How has this changed? Let's start off with Dave Hillman on that one.
I don't know if harsh has changed, but I think maybe we as consumers have kind of changed our expectations. We want the IPC committees went through and talked about high reliability. We want high performance. If it's my kid's toy, I still want it to work. I want it to work a while, but is it life critical, mission critical, safety critical kind of thing? But electronics now, there's a recent graphic about how much electronics is in our cars. And so this invasion of electronics into our lives, we want that higher performance and we want it to work all the time.
Right. Well, that's one of the changes that's happened, of course, is the amount of electronics in cars. But there's a lot of these electronics are expected to work directly on the engine. And so there's a lot of vibration comes into that area there. Chuck, would you agree that the challenges are getting stronger?
I don't know that the specific challenges have changed dramatically, but certainly I would agree with Hillman on the fact that the expectations have certainly changed, and our understanding of what a harsh environment has changed dramatically. For example, probably the most harsh environment that electronics sees today is the human body.
Right.
Implantable medical electronics, excruciatingly harsh, from vibration to a constant temperature. That's that obviously thermal expansion doesn't come into play, but there's a corrosive environment, and it's really a challenge. And then you add to that the expectation of consumer products. The cell phone is the easy, obvious example, but think about all the IoT devices that we're putting around anymore. Mm-hmm. If you spend, even if it's just a few $100s on a security system for your home, you don't want to be replacing it every year or two.
Right.
And some of those cameras are sitting outside in the rain and the wind. Down there where you live, Trevor. What you have to worry about is the occasional, hurricane. But if you're in Minnesota, that thing's going from 110 in the summer to minus 10 or maybe even minus 20 in the wintertime.
Right.
And it has to sell for $50 or less.
Right. Yeah. So, and I think and just for that reason, the price challenges, etc. I guess David Greenman, there's a lot of people aren't coating these types of things. They're looking for other ways of trying to make them more reliable.
Well, yes, and to sort of answer the original question, when I started out in this industry, in the conformal coating industry, it was mainly the military and aerospace that were coating.
Yeah.
And over those years, we've seen it develop even into white goods and even into mobile devices, mobile phones, ear pods and this sort of thing. So it's a different market now. It's a bigger market. And as Dave said, automotive, and especially with EVs, we're now seeing much more, many more boards, many more control boards into the car. You mentioned engine management. Yeah, a lot of vibration, but then you've got braking systems. You've got a whole host of different electronic control boards in there, and they all need protecting from the harsh environments.
Right.
Yeah.
It's certainly a challenge. And what about the temperature extremes? I mean, how have they changed over the years? Let's give that one back to Dave Hillman.
Well, I mean, I spent my career mostly in defense and commercial electronics, but now you're seeing, and once you fire up a bird, the electronics pretty much stay the same temperature, but now you've got them out on the wing. You've got things on pods, on tails. I think we're, like David or Chuck said, we're starting to put things and just leave them out in environments. I mean, here in Iowa this morning, it went from 51 degrees Fahrenheit yesterday to 18 today. So, we've decided we want to put electronics everywhere. We want their convenience. We want the analytical data coming back. Electronics in the fuel bay, in the tanks of airliners, checking on what the fuel's doing and things. Even they're everywhere. I mean, if there's a place that we think we want electronics, that's where it's going. So any environment that's out there now, we're thinking that's where we should be putting it, regardless of what that environment is.
Right. Well, I mean, most of us know that obviously in the automotive industry, we're looking at doing thermal testing to -40 or plus 150. But in these other areas that you're talking about, missiles, aircraft, etc., what sort of parameters do you have to test for these electronics?
At least for the defense and commercial electronics or that side of it, it's still -55 to plus 125. There's always this trade-off between what your accelerated testing and versus what the environments are going to be. And a good example, I'll go back to commercial aircraft. At Collins Aerospace, when I was working there, we tested -55, 125, but the reality was that equipment, at least down in the E-bays, is running at a constant temperature once you turn it on. So you got to take that advanced testing and look back at that environment. But as we delve into deeper environments, you bring up the engine block. A lot of the automotive guys want to see testing to 150 because that more accurately reflects what they're seeing in its life. So, the industry is starting to change those numbers because of how we're expanding. I always think, in fact, the problem yesterday, my tire pressure gauges are not happy with this recent change of temperature. And I'm thinking, those things are just getting pounded every day, all the time. How are they protected? How do they even work?
Yeah. It's true. I mean, and electronics does behave differently as well, with extreme cold and heat and things like that. In fact, we had a discussion, if you remember it, at SMTAI about electric vehicles and how the batteries just seem to die that much quicker the minute they get into that environment. But there you go. Just before I go on to my next question, I just want to say to the audience, if you've got any questions for our panelists today, then please use the Q&A section in below, and we'll be happy to come to these at the end of the debate. So if I move on to Chuck, I mean, what properties does the PCBA need to exist in a high temperature or a high vibration environment?
Well, I guess I would say that one of the things that's important to recognize is that while we see all these new challenges in new environments, our understanding of the behavior of a printed circuit board assembly is far advanced from what it was in the tin lead era. Yeah. We learned more about lead-free solders before we ever put them into practice than we ever knew about tin lead. We just never did the research on tin lead. We'd been using it for 5,000 years, but we never studied it properly. So we know what these assemblies are going to do in almost every environment. And the second thing I would say is that we also know, and I know we had conversations, the three of us, you and I and Mike Conrad at SMTAI, about cleaning as an option too. And no clean doesn't mean there's nothing left there. It just means that hopefully what is left there is relatively benign. But the reality is we're cleaning no clean fluxes now extensively. And then we're putting conformal coating on top of those clean boards. And that's because we understand the environment that the product's going into and the materials combinations that we're using are much better understood. So with that said, I think the reality is that in harsh environments, yes, we are using more advanced materials. Maybe we're using an FR5 instead of an FR4. Cost is a little higher, but it's, in today's world, that cost differential is not as significant as it was, say, 20 years ago, when the cost differential between FR4 and FR5 was maybe 30%. Now it's maybe 10%. So yes, we are using more reliable materials. But again, we understand the materials better. Our multi-layer boards hold together much better than they did 30 or 40 years ago. As another example. So I can ramble on that stuff, but the point is that the combination of understanding the environment that each product is going into, understanding the properties of the materials that are being used, and then taking that into account, with like guys like Dale Lee and use it in their DFM work. They take all those things into account, and now we are capable of designing products to fit into those environments. And the only time you see products that catastrophically fail, I hate to say it, is when you get designs that come from let's just say inexperienced areas of the world where all they're looking at is how much can they cut the cost, as opposed to can they meet the cost and performance requirement.
Right. But the geometry is obviously relevant too, because boards are getting smaller as well. So you're having that. Dave Greenman, I mean, you must. What changes have you seen, or what properties do you think that PCBAs need to exist in these high temperatures or high vibration environments? You've got a range of different coating options that manufacturers can use, but I mean, how would you characterize these, in terms of going from, say, a consumer product right up to a high-end, missile or something like that?
Yeah, I think one thing I would like to just quickly add with reference to the lead-free and cleaning. We've done some work recently, and I know that our R&D manager, Chris Brightwell, I think presented it at SMTI about the effect of vitrified flux on a lead-free, no clean board when you put a coating on the top of it. And of course, today, the automotive industry is wanting thermal cycling -40 to 150, as we've said before, and anything between 1,000 cycles and 3,000 cycles. And one of the things we've found, especially with 100% solids UV curables, is that if there's vitrified flux there, you're going to get mismatch of coefficients of thermal expansion, and you're going to get cracking. So certainly cleaning, I fully support Chuck on the cleaning side. We need to clean, especially today with the fine line technology. If you consider that when lead-free, no clean came in, we were with through-hole technology, radial components, big spacings with track spacings. Now everything's miniaturized. We've got surface mount, and it's so close together that if you don't get a good coating coverage, you can even get dendrites forming on the top of the coating. We've seen this with when people have come to us with problems with other coatings, shall we say, and we've had to solve that. But to answer your original question, Trevor, sorry, I've rambled on a bit. The needs today are far greater than 20 years ago.
Right.
And as I said, the number of cycles of thermal cycling, how many hours? I mean, we've been asked for 1,000 hours of SIR testing. So it comes down to the quality of the finish of the board. It comes down to the solder resist. What's the surface energy of that solder resist? Will it accept a coating? And and as Chuck said, it's all the contaminants are left on there from previous processes when you don't clean. And you're putting a conformal coating on top, and that's trapping those contaminants underneath the coating. And of course, conformal any coatings, that doesn't matter who they're from, moisture passes in and out of them. So if you've got contaminants there, they can become soluble if moisture gets to them, and again you've got a little plating system there. And so we're on our data sheets. Just one final quick thing, and I'll shut up. On our data sheets, we always state insulation resistance. That is normally at room temperature, room humidity, and we quote moisture resistance, which is at 85 degrees Celsius, 85% relative humidity, a totally saturated coating. So that's the lowest resistance level you're going to get. So that's good for the design engineers, especially if they're doing analog type circuits, sensor circuits, to see what potentially the lowest value of SIR is going to be.
Right. Okay. Good point. Dave Hillman, you got anything just quickly to add on the actual properties that PCBAs need to exist in these environments?
No, we've just figured out quality of control has gone up. Laminates have gotten better. Lead-free caused a re-examination of some of the base chemistries. And anytime something, like when Freon went away, and now with the advent of lead-free, it causes a material shift. And like Chuck said, we've taken a different approach to the tin lead world. We're trying to do the work in first and then implement second.
Right. Okay. I mean, Chuck mentioned, FR4 and FR5. Are there other prevalent materials used in high, harsh environment assemblies that where you need absolute reliability? I mean, are you using other types of substrate?
I think that's an interesting question because, when I started early in my career, we used bismuth triazine, easier to say BT laminates, and we've gotten rid of BT laminates. We've gone to FR4 because of the cost. But at the same time, now we start relying on the DFM, look at your layout rules, where conformal coat comes in. So it's more of an ecosystem. If you're relying on one thing, that the board is going to be my salvation to get through this environment, you're in trouble. Put all your eggs in one basket. It's the same thing that's gone on with tin whiskers. A lot of people have gone back to adding conformal coat. They're using it as a mitigation for a new failure mode as a new material system comes into the industry. So a lot of times it isn't, I'm going to go to a more expensive material. I'm going to try to make my ecosystem more compliant to where I'm supposed to go. The down-hole well guys have been using BT and SN96 solder for decades because that's what works for them. And they looked at those material sets and here's my environment.
Right. Okay. Chuck, I mean, is this an environment for LTS materials?
I think the challenge there is what the real life temperature environment is going to be. As Dave Hillman said, once in the electronics bay on an aircraft, once you turn the darn thing on, it doesn't matter.
Right.
And so even if the electronics bay reaches 125 or 130 degrees when the rig is sitting there in the sun, it's not going to be a huge issue for LTS. Okay.
Mm-hmm.
That doesn't mean that it's not a concern. Again, we have the diversity of environments, and the other aspect is that we don't really fully understand LTS yet. You know, we're still in the development stage, so we really don't know what the limitations are going to be today. We're close.
Right.
I would say within the next 2 to 3 years, we're going to see pretty widespread LTS deployment in specific areas because of its dramatic impact on overall assembly technology and cost of manufacturing.
Right.
But we don't have the full picture yet. So is it an environment for LTS? Yeah, it kind of depends. For downhole, probably not.
No.
Not going to work down there. But is LTS suitable for automotive and aircraft applications? Probably for a large number of them, yes. You know, on engine applications, maybe not. But but if you're talking about passenger compartment or you're talking about flight controls that are essentially in a passenger environment, or at worst in a controlled environment that's fairly stable, as Dave Hillman said. I don't see the transition to LTS as being that challenging, but it's going to be more limited than, say, the transition that we went through from tin to lead-free.
Right. And and Dave Hillman, I'm guessing, we're talking by application, obviously low temperature sorters might be applicable, but I'm guessing that's going to be the ones that are not using brittle components, as it were.
Yeah, what's interesting is we've done some work with LTS and we're not finding it really applicable to aircraft, but on the warfighter, it goes back to what Chuck said, what's your environment? I think the more interesting thing is we tried to take tin lead and use that system everywhere. And with lead-free, we're starting to say this alloy can be used for this application, this alloy. Instead of trying to fit everything into one box, we've, as an industry, said, maybe it's time we start specializing and trying not to do it all the same way all the time. I mean, if you look at David's conformal coatings, variety of different conformal coatings for a variety of different, or why take one and make it work everywhere when I can specialize and keep the cost down? So we're coming at, I think lead-frees cause people to take a step back and say, in these harsh environments, should I design differently?
Yeah. Okay, David Greenman, traditionally a lot of these high reliability or high harsh environment assemblies and packages are using underfills. Is that still part of the solution?
The underfills, there's always been a bit of debate, I've found, with regards to underfills as to whether a conformal coating that will partially go under a large package can supplement underfill. And I've over the years had different opinions from different people. There's a client we have in South Africa that doesn't bother with underfills on QFPs, on ball grid arrays, etc. He just allows his coating to flow under, and he says he's never had a problem. And that's, a fairly harsh environment product. So I don't know if Dave has any additional information on underfills. It's not an area that I am particularly expert in, shall we say.
We love it. I love underfills, but underfills are a solution to where Chuck's going to take us, because I'll throw this back at Chuck. I use underfills because the commercial industry is making a package that won't take my harsh environment. Certain BGAs warp too much in their environment. They crack the solder joints, that CT mismatch. So I use underfill to ruggedize for that environment. I look at it as a solution versus I'm trying to use something that maybe came out of a gaming system, or that another company. So it goes back to the component fabricators. They're aiming at where they make the most money, commercial. We in the high performance industry sometimes have to take that product and ruggedize it to either underfill, add conformal coat, a number of things. So it really goes back to where are you sourcing your components and what was their original intent for that component to be. And a lot of times it's not for the high performance industry.
Right. Chuck?
There's a lot of tailoring going on is really what happens.
Yeah.
And I think that goes back to the point that I think we've been reiterating. And I know I'm a little repetitive on it maybe, but the diversity of environments that we're going into, and they're all harsh. Pretty much. There are very few benign applications anymore. As Dave Hillman started off the discussion around, even when you're talking about Christmas toys for your kids, if that, we used to live with toys that broke on Christmas Day. We don't anymore. If it breaks on Christmas Day, it goes back to the store.
That's
right.
The retailers don't want to deal with that. The manufacturers don't want to deal with that. Nobody wants to deal with it.
Right.
So if you look at it from that perspective, there isn't a single electronics application that isn't in a harsh environment. I mean, I can't think of a harsher environment than a 5-year-old kid.
Oh, when I was a 5-year-old kid, we used to get toys from made in Japan, and we'd expect them to break. You wouldn't expect it today, that's for sure.
But I think I think Dave's point is well taken and on the underfill thing. It's like I remember when Walt Marcinkiewicz, who was at Ericsson, presented a paper talking about how they had discovered that on chip scale packages, which we don't even call them that anymore, but with chip scale packages, what they did is they found that if they covered the whole bottom of the package with balls, even if they only needed 50 or so, they cover the whole bottom of the package with balls for one purpose: drop shock. That was it. That they didn't have to underfill if they covered the whole bottom of the package. So they could put all these empty ball pads on there that didn't connect anything. Well, guess what? Today we don't have any pads that are not connected to anything. The density of our packages and the density of our chips is so high that they're all covered with nothing but balls on the bottom of the packages anyway.
Yeah.
And so you can, in one environment, as Dave Hillman just said, in one environment, you throw them on the board. Another one, you have to underfill them. And another one, you have to underfill and conformal coat. So you have to look at that environment.
Depends on the application. So, I mean,
management's another issue, Trevor. How you manage the heat. I remember when the Xbox first came out. I don't know if you remember that, but Microsoft lost almost $1 billion in the first year and a half on the Xbox because they were failing after 2 weeks.
Yeah,
because they designed the product for an 80% duty cycle, and the kids figured out how to make it run automatically all day long. And so when they were at school, it was running. And at 100% duty cycle, it failed in less than 2 weeks. And it was because the heat sink on top of the graphics processor wasn't big enough because the disk drive sat just above it.
Wow.
And they redesigned the whole Xbox, and they were replacing Xboxes for free for a year and a half. And
I know some companies that made a lot of money out of that actually, but yeah. But talking about heat sinks and these thermal excursions, I mean, of course, the LED industry is famous for that. The systems behind all these LEDs are massive heat sinks to try and take away the heat. Dave Greenman, we have spoken for years about the number of people actually doing conformal coating, and I remember at one time it was largely thought that about 20% of companies that were doing conformal coating were actually cleaning underneath these assemblies. Has that gone up in recent years?
Cleaning in itself, no, obviously with the advent of no clean, we saw a decline in cleaning, but what we're now seeing is people coming back to cleaning. And, especially in the high rail areas. I mean, the military, as far as I'm aware, Dave, have never
Clean.
stopped cleaning.
Right.
They've always cleaned before conformal coating. And, you know, that tells you something. Those guys need long reliability. They need 20 years in storage, and then they need it to come out of storage and, pardon me, but go whiz bang and function.
Right.
And so it's something which we're seeing more of now, cleaning. And obviously there are like the likes of Zestron, etc., and Kaizen are all developing materials now that will clean and clean underneath components, because you do need, when you're cleaning, you do need to get that flux, etc., out from underneath.
Absolutely, you know, and there was another whole problem there with the low standoffs. But what
Yeah.
about the conformal coating side of it? I mean, does everybody who's involved in doing harsh environment assemblies should they be applying conformal coatings?
Well,
I know
yeah.
you can say yes to this. But
Of course, I would say yes. What else am I going to say? Yes, certainly. If it's high rel, if it's going into a harsh environment. I mean, if you'd asked me 5-6 years ago if the mobile phones would have some form of conformal coating on, I would have said, I would have laughed and said, you must be joking.
Yeah.
Now, yeah, they've either got selective coating or they're using a ultra thin coating, as the IPC calls it. So yeah, it's because of the nature, as I said earlier, of the packing density, the fine line technology. Coatings are becoming more and more necessary to, you know, protect against harsh, even, you know, just walking out of your house with your telephone, you know, from 25 degrees out to -5 or whatever, you know, you need a coating.
Well,
John.
Trevor, it's kind of funny because you think about it, again, it goes back to us as consumers, the ultra thin coatings. Why did they show up? Not because NASA needed them on the moon. We like to take our cell phones into the bathrooms and they drop into the toilet. I mean, of all the reasons to get a new material into electronics, and we drove it because of our habits. So sometimes the harsh environment is, you know, something you never imagined. All those ultra thin coatings came about for, to me, it's like, really, is that how we got into this part of the world? And they did.
Yeah. Well, you know, as you said, as you said earlier, Chuck, I've been living in Florida a lot. I lost 2 cell phones in swimming pools in the space of 3 months. but Chuck, just a quick question. I mean, are there any situations where you wouldn't need to coat in a harsh environment?
In a harsh environment, I would say one example would be in a large number of implantable medical electronics, because those typically do not go into an environment where the electronics itself is exposed to the chemistry of the body. They're pretty much encapsulated. Okay. So and in that kind of an application, you know, even a millimeter or 2 of coating is expensive, in terms of miniaturization. Speaking of miniaturization, I think that's part of the point too, is that while we've certainly expanded dramatically the number of quote harsh environments and the types of harsh environments we enter, miniaturization has helped alleviate that problem as well, because miniaturization reduces the mass, which reduces the susceptibility to things like drop shock. It also, miniaturization tends to reduce sensitivity to CTE mismatch. Obviously, as Dave Hillman pointed out, if you're taking a big video processor from NVIDIA and using it in an aerospace application, that's a different ballgame. But when you're talking about really truly miniaturized electronics, where you don't really have a big, large, complex processor, but you have a very specific application, like a security system, you know, those boards are minuscule. So CTE is not a concern in that kind of application. And so there are applications where I think that, those types of applications where you don't need a conformal coating. But I think that, certainly, I put together the programs here for the Northwest chapter, for Oregon chapter.
Mm-hmm.
And one of the hottest topics is always conformal coating.
Right. Yeah, that's true. One quick question going back to you, Dave Greenman, on coatings is in these harsh environment conditions, is plasma treatment advisable to sort of provide the maximum amount of coating adhesion?
It certainly helps. We've done some trials ourselves with our classics, which are solvent based, and with our 100% solids UVs. And certainly plasma assists in adhesion. But I do not consider it an alternative to actually cleaning the board properly.
Okay. Dave Hillman, is voiding a reliability issue?
Oh man, one of these days that whole topic will...
issue, or is it no issue at all?
I'll take a Doug Paul's answer as it depends, but the reality is voiding on its own anymore really isn't an issue unless it's a design attribute. I'll go back to, you brought up LEDs. LEDs need to get the heat out of them, and they need to get it out all the time. And so if you have voids there, you have an issue. And that has led us to see inline vacuum ovens and vacuum assisted vapor phase type of systems for soldering. But the reality on BGAs, the IPC did a huge study, and Collins Aerospace and Lockheed Martin, a number of the industry, the high performance companies were part of it. Until the voiding gets big enough to where you hardly have any solder there, it really isn't an issue. That solder was going to fail. That's where it wanted to fail anyway. The void did not blunt the crack or make the crack go faster. So, and we're found the same thing. The last 2 years of publications at SMTAI have shown that for QFNs. If the QFN, that thermal pad, needs a certain amount of heat transfer, you better not have the voids there. Otherwise, it's back to good process control. And the addition of X-ray is going to cause the industry to do further studies. I know of one study going on right now of voids in chip resistors and chip capacitors, because people are seeing that when they do an X-ray inspection, and they've asked the question, is this void good or bad? And we just need to take the time to get the data. But if you look at BGAs and BTCs, or bottom terminated components, it's a component attribute that we're worried about. The solder is fine. That void comes down to, is it going to affect the performance of the component?
Right. But does the location of it, I mean, if it's right up close to the intermetallic, for example, is that not a bigger issue than if it's in the middle of the bowl?
I haven't seen that. At least my experience and the testing I've been part of have not seen that. It really comes down to what stresses were you under? I mean, we've taken parts and had the one study that's been out there, the last will and testament of the BGA void paper we did years ago. It's got, I think, 3,700 reads on it now. That part was going to fail. That a BGA ball that is 40% voided has a solder ball next to it, and the crack was in the solder ball without the void. The voided solder ball didn't have a crack at all. So the voids are more, we as assemblers need to make sure we have good processes. We're getting low voiding paste. And that's probably the biggest issue, is the lead-free solder paste suppliers are still evolving on getting to where we are today with tin lead voiding paste versus lead-free voiding paste. We need them to step up, and they'll get there. They're still working on their chemistries.
Right. Yeah. Chuck, have you any views on the voiding issue?
I'm with Dave Hillman. It's really not so much of an issue, and the reality is that the voids are as he's pointed out, are a result of the chemistry and of the flow properties of the molten material. Rob Rowland and I right now are actually working on a white paper to talk about what is a good solder joint. Because one of the issues that we have with solder joints in general is that solder joints we don't tend to see them as as metallurgical components. We tend to see them as visual components. And so whether we look at them optically or with X-ray, doesn't really matter. We're still looking at something.
Yeah.
And the look is really almost irrelevant. What really matters is the microstructure. Do we end up with very fine grain structure or coarse grain structure? Do we end up with a thick intermetallic on one side and thin on the other side? Do we end up with contaminants trapped in the middle? Do we end up with a homogeneous solder joint? It's the metallurgy that matters, not the visuals. So X-rays and optical inspection really are merely nothing more than mere demonstrations of what we hope is inside the solder joint. So we have to find ways to really know what's going on inside instead of talking about what it looks like.
That's true. I mean, for years we didn't even know they existed, you know, and we went on, we soldiered on aimlessly, you know. We actually started to see them to say, you know, to start getting worried about them, you know.
A solder joint doesn't need to be shiny to be perfectly good. Yeah, it makes no difference.
Yeah. All right, my last question, and it's a rather tongue-in-cheek one. It's is returning to through-hole components the best way forward? We'll give that with you first, Dave Hillman.
Oh, well, you know, through holes, we all view it as indestructible, and it is. We did a recent test to understand the effects of nickel on the total. We're chuckling. What's, you know, the nickel limits on our solders were kind of out of whack between the J standard 6 and the industry contamination table. So Collins Aerospace did a large study, and of course it's through holes where we wanted to look at it. But it took 8,000 cycles. It was 2 years of thermal cycling to get anything to fail. So you had any kind of statistics to understand, is it there? So I still, you know, and you had mentioned we've gone to surface mount, yet we still have through hole, you know, and there are times when the through hole, you need that bulletproof. I'm going to put it someplace and I don't want to worry about it. Yeah, you see a lot of through hole in harsh environments because of that attribute. So it's always going to be here, you know, but it is sliding into a very specific niche rather than it's no longer the widespread creature it was.
Yeah. Okay. Dave Greenman, you got any thoughts on it?
Well, the thoughts I have on it is that in the days of through hole, the only concern with regards to coverage was on the print side of the board where the wires were chopped off. Nowadays, with surface mount, with square components, sharp edge coverage on those component corners is a problem. And it's something that we've certainly been addressing and have solutions to. And as we get, you know, increased packing densities, there's more chance of problems arising. So that's the way I look at it. If we went back to through hole, yeah, from our point of view, life's easier.
Okay. All right, so final word is going to go to Chuck, but before we do that, I just want to remind our audience, please, if you have any questions, please put them in the Q&A box and we will address them very, very shortly. So please think of your questions now, and I'll move to Chuck now just to get your view on is there any advantages to using through hole?
Well, is there advantage to using through hole in terms of reliability in harsh environments? Yeah. Is there a likelihood that we're going to move very far in that direction? No. I mean, I'm going to date myself because I've been around long enough to remember. When I started in the industry, David, there was only one product called Humiseal. You didn't have a catalog.
No.
You had one. It came in 4 different size cans and a barrel. There was one product. And,
absolutely.
You know, and we were still using wire wrap boards for prototypes at Tektronix when I first started. Now, wire wrap is, by the way, is still a great technology. It's very reliable in harsh environments, for example. Combined with through-hole components, wire wrap is really a very good, inexpensive way to build a reliable product. But my point being, the chances that we're going to move very far in the through-hole direction is, I think, the only area that we're likely to see some through-hole stick around for a long time is in harsh environments, and it's mostly going to be the connectors. It's not going to be very many. There will be other devices, but mostly the connectors. In consumer products, even the connectors have gone to surface mount now.
Yeah.
So I would say not likely that that's the right answer.
Okay, great. Well, I can see the sun's come up in where you are in Oregon, because you've certainly got a lot brighter. That's good. So I think it's time that we're going to move to the Q&A, and there's not really much in there, but we'll go to the Q&A. We've got a quick question from Anthony Raffanelli asking who the guy from Humiseal is. It's David Greenman, is of course who it is. And
That was a tongue-in-cheek question.
it was, but yeah, I mean, and he says it's all about engineering a solution for specific use case or environment, which it is, of course. I've got one question that I might put to you guys, and that is additional question. That is, Chuck, you've been doing a lot of work on heterogeneous integration at the packaging level. Do you think that's something that needs to get extended into the board level at some point? I mean, would that help with reliability, and if we have a heterogeneous approach to the materials that we used at a board?
I think I would say that yes, and I think that we're already seeing that actually. And when you say heterogeneous, I guess it depends on exactly what you mean. But if you look at the way that we're building products today, we are using a variety of approaches.
Mm-hmm.
In some harsh environments, for example, some of the sub-assemblies are being done on ceramic substrates using tin gold as the solder, because you can't rework it, but once you've soldered it ain't going anywhere. Okay, and so you can use those kinds of approaches and use a tiered level of assembly technology to create that structure, and put the money into the reliability of those sections that are most vulnerable and most critical.
Yeah, sounds sensible. Dave Hillman, any thoughts on that?
I think the one thing that I experience and continue to experience is, trying to get, we get in a large VGA, 2400 IO, and that's because it has multiple die in it. And that's great. The functionality of that part is absolutely spectacular. It's 2400 IO. Statistics are not my friend. All I need is one solder joint to be bad. So, at least from my viewpoint, I've pushed back on the component fabricators and say, hey, can't you do die integration? I mean, I know what it takes. I know it's expensive and things, but, we've gotten to the point where it's one of the reasons for the low temp solder alloy emphasis. Parts have gotten so big, we can't assemble. If you can't build it, you can't use it. So, you've got to go back. We lean on our component fabricators to be innovative, to try to get the packages back down to be smaller. Going smaller was one drive, but just integrating that functionality into a die at prices they believe that are supportable, that also helps us on assembly. So it's this back and forth. You see, you finally hit that point where I'm too big, we're going to fall off the cliff. And so I always look back and what can my component fabricators do for me to get me back into my sweet spot of assembly and high yields. Right.
Excellent. Okay. Well, gentlemen, I think we've pretty much come towards the end of today's panel. I want to thank you all for some great input and a good debate. And you all played nicely. I didn't have to break anybody up. So I want to say a very big thank you to David Greenman from Humiseal, of course, and to Chuck Bauer from TechLead, and of course to Dave Hillman from Hillman
Electronic Assembly Solutions.
Electronic Assembly Solutions.
Yeah, EAS, it's a whole lot easier.
Okay. That's it. So thank you, everybody, and thank you to our audience for watching today.
Young is leading a smart revolution that will change the world of electronics manufacturing. Based on our pioneering True 3D measurement-based inspection technology, we revolutionized the solder paste inspection market to such great lengths that 1 in 2 SPIs sold today is from Young. Building our SPI technology, we expanded to automated optical inspection, also known as AOI. Every year, we introduce new award-winning innovations and have proudly earned the respect from thousands of customers across diverse industries. Aside from our R&D center in Korea, we have research facilities focused on artificial intelligence and deep learning across the world to help us further develop proprietary AI technologies for your challenges. With our global network of sales and service centers, we aim to respond quickly to your needs and to deliver the highest level of customer satisfaction.
Global SMT and Packaging opens the windows of the world to bring you the latest news and technologies from Munich, from Bangalore, from Shanghai, from San Diego.